Hi everyone, thanks for listening. This is Qixia. Me and my colleagues Zeyi and our PhD advisors Xun Li are from College of William Mary. Today I'm going to present our work ToFi. It is an algorithm to defend against Byzantine attacks in federated learning. Here is the outline of my presentation. In this presentation, I will introduce a naive algorithm and modify it to a self-adaptive two-filter algorithm, ToFi. So let's get started. Right now, the deep learning model becomes more complicated for practical tasks such as computer vision, natural language processing, etc. Therefore, a distributed framework is needed for using the computational resources from multiple machines to train a global model. Federated learning is a collaborative training process for multiple workers. It is widely adopted in practical implementations. We can use this figure to illustrate how federated learning works. As we can see, in federated learning, here we have one parameter server and several workers. First, for privacy concerns, the primary server does not keep any data. Instead, each worker keeps its own local dataset itself. In each iteration, the server first randomly selects some workers to perform computations. In this figure, we select worker 1 to worker M among n workers. Each selected worker will grab the current model parameter from the primary server and perform gradient descent based on their local dataset to get the update weight Wt plus 1 I and send the updated model weights to the primary server. The server aggregates all the received local update weights to update the global model by taking the average of them, and then we finish one iteration. However, Byzantine failures may happen when some workers cheat or are under attacks. We can see in this figure, worker 2 is a Byzantine worker. When this worker sends the local update weight to a server, instead of sending the real computational results Wt plus 1, 2, it sends something malicious, Wt plus 1, 2 bar, which is not equal to Wt plus 1, 2 to a server. Here we use Wt plus 1 I bar represents the update weight that parameter server received from worker I in iteration T. If it is equal to Wt plus 1 I, it means worker I is honest in this iteration. Otherwise, worker I is a malicious Byzantine worker. Because the parameter server simply takes the average to aggregate the received weights, the global model can easily be manipulated by the Byzantine workers and make the whole training process incorrect. Therefore, our goal is to design an algorithm running on the parameter server side, such that even if there are Byzantine workers in the training process, we can still make the whole training process correct. The input of our algorithm are the update weights uploaded by each worker, and the output is the updated global model. However, although federated learning is a special kind of distributed learning, there are two major differences compared to distributed deep neural networks, which makes the previously proposed algorithms does not work well in federated learning. First, the distribution of the dataset in each node may be different because data heterogeneity is an important feature of federated learning. So the dataset is non-ID. Second, it is possible to have malicious majority. Here, we theoretically define the two differences in federated learning scenario. Assumption 1 basically defines the heterogeneous environment. This equation here defines the local update is based on the stochastic gradient descent on its local dataset Xi, and Xi is based on its own data distribution Di. We know that in federated learning, each worker keeps its own private dataset. So this assumption here means local updates are based on its non-ID local dataset. Assumption 2 defines the Byzantine environment in federated learning. Here we let BT represents the set of Byzantine worker indexes at iteration t, then we can assume that the worker may become non-Byzantine worker or Byzantine worker at different iteration. And the number of Byzantine workers in each iteration can be arbitrary. So federated learning has this condition because although we can still make the similar assumption that the honest nodes are majority in federated learning scenario, but in each iteration, we cannot assume that there are more honest nodes in the random selection. For example, assume we have 100 workers totally, and 30 of them are Byzantine. In each iteration, the server randomly selects 10 nodes to perform computations. We cannot ensure that there are more honest workers than Byzantine workers in these 10 selected workers. There are some previous explorations about defending against Byzantine attacks in classic distributed deep learning. In summary, there are three directions. Score-based algorithms such as Cron, Zeno, Zeno++, they aggregate the model by giving scores to each updated information. Median-based algorithms such as geometric median, median around median, coordinate-wise median, they aggregate the model by using the median instead of the average. Distance-based algorithms such as Vevo, they conduct the distance information to remove the outlier update information. However, all these methods have a common core idea that the honest update information is majority, and the IID dataset condition makes them close to each other. So they can use this observation to remove the outlier Byzantine update information. As we said, these conditions are not feasible in federated learning. Therefore, we propose our algorithms to solve Byzantine problems in general federated learning. In summary, here are our contributions. We propose a reference dataset-based naive algorithm and modify it to a self-adaptive algorithm ToFi, which can run efficiently on the server side and is very effective for defending against Byzantine attacks. Our algorithm is the first work to address Byzantine problems in federated learning. Unlike classic distributed machine learning, here we assume dataset is non-ID and it is possible to have malicious majority, which makes the previously proposed algorithm ineffective in this scenario. We use experiments to show that our algorithms are the only existing algorithms that can solve Byzantine federated learning problem. We first introduced the naive algorithm based on the reference dataset to defend against Byzantine attacks. Here we first assume that the primary server holds a small but representative reference dataset. Let Xi be the reference dataset. Then Xi is randomly sample of the whole dataset distribution. We would like to use this representative reference dataset to check the contribution of each worker on minimizing the loss of the whole dataset. This naive algorithm uses an alpha-weighted average to aggregate the received model parameters. Assume each machine uploads its computated weights Wt plus 1 I bar. The primary server will use an alpha linear combination of all uploaded weights to get a new weight in time t plus 1. And the sum of all alpha I is 1. In order to solve this alpha weight, we simply minimize the loss on the reference dataset. The idea of the naive algorithm is actually easy to understand. Because we minimize the loss of the weighted average weight on the reference dataset, which is the same distributed as the whole dataset. Then if some Wt plus 1 I bar are uploaded from malicious machines, they will be given a less voting weight because the malicious information must contribute less on minimizing the loss on the reference dataset. If it doesn't, even if this information is uploaded from a Byzantine worker, we can still think it as a good information because it contributes more on minimizing the loss. The naive algorithm is described here. It actually minimizes the loss of alpha-based linear combination on reference dataset KCR to solve this alpha I. And we use the solved alpha I to aggregate the weights to get the global weight at time t plus 1. This naive algorithm works because if we think of the ideal case when the reference dataset is exactly the whole dataset, in each step, the ideal scenario is that we can delete all the attack updating information and only use the honest updating information for the aggregation. The alpha weight linear combination actually includes this scenario. So, in fact, in each step, this naive algorithm can perform better than the ideal solution. And this shows the feasibility of the naive algorithm. We also proved the convergence of this naive algorithm. Here we made two assumptions. First, we assume FW is Lipschitz continuous. FW is the loss of these neural networks. Second, let this nabla FW be the gradient among the whole dataset, and nabla FW be the gradient among the reference dataset. Let theta W be the angle between them. Now we assume theta W is no more than theta 0 and theta 0 is smaller than pi over 2. This is possible because we know that the reference dataset is a random sample of the whole dataset. Therefore, it should have the similar performance with the whole dataset. With these assumptions, we can prove that for arbitrary small epsilon greater than 0, we can find a delta greater than 0, such that for any step size gamma that is smaller than delta, let phi be the angle between the equivalent aggregation gradients and the true gradients. We can have phi smaller than theta 0 plus arc cosine 1 minus epsilon almost surely. This actually ensures that we can bound the angle between the aggregation gradients and the true gradients for small enough learning rate. We can use this lemma in Boto's online learning structure to prove the convergence. However, for this naive algorithm, there are two shortcomings. First, the performance of this naive algorithm really depends on the quality of the reference dataset. If the reference dataset fails to represent the core distribution of the whole dataset, the performance will downgrade a lot. Second, in order to solve the minimization problem, we should use gradient method or gradient descent. Both algorithms are very time-consuming and therefore are not feasible in practice. So in order to mitigate those shortcomings, we propose ToFi. The core idea of ToFi is to use the normalized loss to remove outlier weights and use the softmax function on the examined loss to approximate the minimization alpha weight result in the naive algorithm. Here are the main steps. First, we use the reference dataset as an examination to calculate the loss based on the model parameters uploaded by each node. Then we simply filter out those parameters who result in too big loss. Those model parameters are outliers and contribute very less on minimizing the loss. We also provide a coarse filter for the extreme scenario when all participating nodes are Byzantine. In this scenario, we simply compare the projected gradients with the previous iteration projected gradients so that they do not differ much. In the end, we use a softmax function to assign alpha weight to each parameter. This can approximate the alpha weight based on their loss contribution and can approximate the minimization results very quickly compared with the naive algorithm. Here is the description of our ToFi algorithm. In this algorithm, two filters are proposed. The first filter is reference dataset-based loss filter. This filter uses normalized loss to remove outlier and uses softmax lag function to decide alpha weights. The second filter, we call it update similarity-based filter. It is actually a coarse filter and can be rarely used in practice, so we can set it very loose. We simply set a similarity function to compare the adjacent iteration gradients. If they differ too much, we remove those gradients. In the experiment, we set it like this function. It actually compares the norm and angle that do not differ much. We can also use other functions. By using these two filters, we can filter out the malicious information almost surely, and thus we can defend against Byzantine attacks in federated learning. We conducted several experiments to show the performance. This is the experiment result on all-node participation, enhanced heterogeneous environment, CIFAR10 dataset, and Byzantine ratio of 0.3. We can say that only ToFi and FEBA are capable of defending against the Byzantine attacks in this scenario. And the ToFi performs slightly better than FEBA in Byzantine environment. And the FEBA is a little bit better than ToFi in non-Byzantine environment. This is because in non-Byzantine environment, the losses for all nodes are similar. So ToFi may filter out some useful information by both filters. Crime and geometric median have really low performance in this environment. This is the experimental result for majority attacks. Here we adjust the Byzantine ratio to 70%, and we use all-node participation, naive heterogeneous environment, Gaussian attack on CIFAR10 dataset. It is obvious that crime, geometric median, FEBA cannot defend against majority attacks. Only ToFi is still able to defend this kind of attack. It is because those methods are not designed for majority attacker scenario. So the majority attacks will take over the training process and make the whole training incorrect. In the end, we conduct experiments for partial node participation federated learning with enhanced heterogeneous environment, Gaussian attack, CIFAR10 dataset, and the Byzantine ratio of 30%. Here we use totally 100 workers, and each time 10 workers are randomly selected to perform computations. We can see that ToFi outperforms all the other algorithms. It is because those algorithms are not designed to deal with the two differences we discussed in federated learning. When the distribution of each node's dataset is not IID, and Byzantine nodes may take majority in some iterations, the performance of those algorithms downgrades a lot. So in summary, we proposed a naive algorithm and modified it to a practical algorithm, ToFi, to defend against Byzantine attacks in federated learning. Our algorithm is more effective than previously proposed algorithms and are very efficient. We investigate the differences between classic distributed machine learning and federated learning. Our work is the first work to address this problem in federated learning, which has more general conditions. We conduct several experiments in various environments to compare ToFi and other existing algorithms to show our superior performance of defending against Byzantine attacks in federated learning. That's all for my presentation, and thanks everyone for listening. I would like to take any questions you may have.